Hi there, I want to take you through a little journey in this lesson on the life cycle of stars. Now before we begin looking at stars, we have to kind of look at the very beginning, which is the Big Bang. The current theory of cosmology is we have a Big Bang, and as time goes on in the very early stages, as the universe cooled down from this huge explosion from a singularity, we had quarks, protons, electrons, other crazy bits come into the mixture as things cool down. Eventually we have hydrogen atoms, which is a proton, is the nucleus, the electron come round the proton, and that was it. Okay, that was the universe in the early stages. So how do we have galaxies and stars and planets and all these strange things? Well, it all comes from these, okay, hydrogen atoms. So I want to imagine a huge big universe just filled with nothing but hydrogen gas, or little pockets of hydrogen gas. And along comes a little bit of a disturbance. Okay, so let's imagine this bit here being just hydrogen gas. And then you have little areas where it's more dense and less dense than others. Then you have these disturbances perhaps. Then you have some of that gas coalescing to form more dense regions. As that gas becomes more dense, it becomes hotter, but it also becomes more gravitational. It has a stronger gravitational pull, and it begins to pull more and more hydrogen gas towards it. And this is what we call a protostar. It's not a star yet, but it's a ball of hydrogen gas which is getting hotter and hotter, and it's attracting other hydrogen atoms towards it to make it more dense and more massive. You can see it barely. It's not super bright like stars. Often like this, it's surrounded by other bits of hydrogen and dust, so you can't really see this protostar in the middle. But the idea is that this super dense ball of hydrogen gas is getting more dense and more dense and more massive and hotter. Eventually something happens. Okay, so I want to take you to this, and I want just to discuss really quickly about nuclear fusion. Nuclear fusion is when hydrogen, let's keep it simple just now, there's a few other sort of quirks to it, but nuclear fusion is hydrogen atom and hydrogen atom, and they combine to give helium. There might be another few stages in here where you have different isotopes of hydrogen, but let's just consider this just now to be two hydrogens make a helium. And there's some radiation and things that come off, but for the moment it's just that is the simple picture. So if we go back to this, the universe, we go to hydrogen atoms, and then how do we get different things, different atoms? Well, we need some nuclear fusion, and there are different ways in which you can make this happen. For example, the word is called confinement. And this really, the pinnacle, the search, the holy grail of energy on Earth, to make this energy, because this process here, this fusion, gives out a lot of energy. And it just so happens that the energy follows this equation here, but that's a story for another day. So how do we get this confinement where these things become close enough that they're able to fuse together? Well, you can do it in various ways. You can have magnetic confinement. You could have optical confinement, that's big, huge, powerful lasers. You could have pressure, and that's going to be nuclear bombs. We have a huge implosion causing these to fuse together. With that comes temperature. So pressure, temperature, you're forcing these things together because they're so close together, they are confined together. But we're looking at this one here, gravitational confinement, and that is the basis for stars. In a star, in this protostar, where you have this ball of gas getting more dense and more dense, in the center of it, it gets more dense, it actually gets hotter. And these hydrogen atoms in the middle of this protostar are so close, and they've got such a high temperature, in other words high kinetic energy, that they're so close they can actually be fused together to form helium, and that makes the protostar become a star. Okay, so a protostar is when it's getting hotter and brighter. Okay, this image here in the YouTube video is a bright ball, but it's not a star yet. It's a protostar. It's a ball of hydrogen gas where it's getting more dense and hotter and more massive. But eventually, this process of nuclear fusion will happen because of the gravitational confinement. It's so hot in the center that hydrogen fuses to become helium, and then at that stage the protostar becomes a star. Okay, so I want to bring this picture in now. This, I'm afraid, not afraid actually, this is great. This is what you need to know for GCSE science. Let me just put a bit of paper down to avoid the glare. So this diagram here is something I would like you to learn, to commit to memory, to understand. Here we have the protostar. This is your ball of hydrogen gas. Remember, it's not fusion yet, so it's your hydrogen gas, it's not fusion. And then when fusion happens, when it's really hot and really dense, that fusion can happen, then the protostar becomes a star. And what's really cool is a lot of the dust that's around it, that's part of the protostar, gets blown away because of the energy released from this newly formed star, and those particles can go off to form parts of the solar system. In fact, that's how planets come about. A lot of the dust in the gas forms planets. Now, we have a choice here. As you can see, the protostar can either go this way or it can go this way. So we have a choice of two different paths. And for most of the stars in the universe, in the galaxy in particular that we know of, it will go this way. In fact, our sun is quite dull. Not dull as in, it's just quite a boring star. It's not too big, not too small, it's not too hot, not too cold. It's just average. Okay. Most of the stars in the galaxy that we know of, we can see, are actually smaller than our sun. We'll discuss them in a second. So these are stars about the same size as the sun or smaller, but we're going to discuss typical stars about the size of our sun. Sometimes they go here, stars much bigger than the sun. So the first thing we have to learn about is after the fusion happens in this protostar, we have a star. What makes it go this way or this way? It's all to do with the initial mass of the protostar. A huge protostar, which has got lots and lots of hydrogen gas, will form a large star. A smaller protostar will form a smaller star. Now, in the protostar stage, how long does this gas spend in this stage where it's gathering more gas, making them hotter and hotter? It's about 100,000 to about 10 million years in this protostar gathering hydrogen gas. Okay, that's the sort of the time scale. It's really long. Sometimes quick, sometimes much longer. Okay, before it becomes a star. But once it's become a star, we talk about it joining what's called the main sequence. And I want to show you this here. Let me just go to it quickly. This one here. So that's the diagram that I'm going to give you tomorrow in the assignment, or today in the assignment I should say, but this is quite cool. Okay, this is called the Hertzsprung-Russell diagram. It is sort of a picture reference of all the stars that we can see, or most of the different types of stars that we have seen in the galaxy. There's two y-axes and one x-axis. The x-axis is surface temperature. Now, over here, it's quite odd, over here is cooler than over here. So we start off with cooler stars, over to hot stars. Now the units are Kelvin. Let me just briefly explain what Kelvin is. The Kelvin scale is the same number of divisions as degrees Celsius. Okay, but 0 Kelvin, which is the start of the scale, is the same temperature as minus 273 degrees Celsius, and that's called absolute 0. There's a decimal place after that. It's a theoretical value that we can never get to. We can get to within a few nanokelvin of this value here, for various reasons why we can't get there. But the scale starts with 0 Kelvin, which is the equivalent of that one there. So room temperature, which is about 20 degrees, would just be this number here, add 293. So it's 293 Kelvin. A lot of the physics equations that involve temperature will involve the Kelvin scale, not the scale. But please also note that the divisions are the same. So 1 Kelvin is the same temperature rise as 1 degree Celsius, but the scales start at different values. So when we look at stars that are around 5,000 Kelvin, we're really looking at stars that are 4,727 degrees Celsius. In other words, it's pretty hot. Okay, that's hot, the big numbers. Okay, so please don't get too confused by the units, they're just big numbers. So we're dealing with things like 2,500 Kelvin up to 30,000 Kelvin. That's the surface temperature. Inside the star, we're looking at much higher temperatures. And what I want you to notice here is there's a bunch of letters. I don't know what the letters stand for, but I do know that our sun, which is right in there, is given the code a G2 space V star. Don't know what that means. It's a yellowish star of reasonable size. And you notice that the stars that we can see and observe follow a line. And that line is called the main sequence. That's an important word, it's an important phrase I want you to know, the main sequence. When a star, because it's formed from a protostar, it becomes either over here, it doesn't matter which side, it forms or it becomes what's called a main sequence star. Okay, in other words, depending on its mass, which again depends on what the initial mass was, depending on the initial mass of the star, that determines not only its size but its brightness and its lifetime. That's an important thing there. So these stars down here, these are called red dwarfs, the M and K class stars. Those are small, they're also quite cool on the surface. They're not very bright, in fact they're hard to see, and so I should just mention this is luminosity based on the sun. So if we take the units of one sun being here, that's number 1, then these stars could be 1,000 times less luminous than the sun. This one here is called absolute magnitude brightness. That's just another way of describing the scale. In other words, the higher up the scale you go, it's really bright, the lower down, not so bright. Okay, so please don't stress about the units, just think about it as sort of dim or dull, bright. Okay, that's the way the scale goes. So these are red dwarfs, they're quite cool, they're quite dull, they're quite small. These stars we reckon would last or be in the main sequence for about 100 million, sorry, wrong number there. These red dwarfs would be on the main sequence for hundreds of billions of years. Whereas stars here, including our sun, we reckon have a lifetime of about 10 billion years. And these ones over here, these blue stars, which are really bright, quite massive, we reckon these ones have a lifetime of around 10 million years, maybe a little bit more. So the smaller, cooler, dimmer stars have a long lifetime, the medium stars have a medium lifetime, and the big, bright, blue, hot ones have a short lifetime. Now why is that the case? Well, let's have a think about what happens on or to a star in the main sequence. So let's just go over here for a second. If you take this as the star, then the star is mainly made from hydrogen gas. Put hydrogen there. But in the centre of it, where it's the hottest and the most dense, you'll have this gravitational confinement. You're going to have the hydrogen gas fusing to be helium. That fusion process brings with it energy or pressure, and so that fusion reaction causes the star or the gas to be pushed out. So that's that's called pressure, and that's from the fusion, from the energy of the nuclear reaction. But at the same time, remember, what happened to the protostar was the huge amount of gas has its own gravitational pull, and actually the gravity pulls it in. Now when a star is in the main sequence for however long it's there for, hundreds of billions to 10 billion to tens of millions of years, this happens, and it's called hydrostatic equilibrium. You don't have to know that word, but I want you to know it just because that's what happens in a star. So for a main sequence star, this happens for its lifetime, or its recognisable lifetime, as we see the star looking reasonably stable. Obviously in the surface you have solar winds and magnetic fields and all these strange corona effects, but it's pretty stable for the lifetime on the main sequence doing this here. The outward pressure of the fusion is balanced by the gravitational pressure of the mass of the star, and it's in balance. Okay, so that's the image of why stars are stable on the main sequence. Now, what happens when a star no longer stays on the main sequence? Why would that happen? Why would the star suddenly not be on the main sequence? Well, what happens is the hydrogen gas available to the star near the centre, where it's the hottest and most dense, that runs out. And so if you look at the diagram, if we were to stop the fusion pressure, then what would happen is the star begins to collapse in on itself. Now, something happens with that, because this helium core, as the star collapses, actually becomes hotter in the middle, more dense, allowing helium to fuse together to form carbon and some oxygen. So that brings with it something else, because when that happens, this fusion pressure will become even greater. And what happens is that regular boring star, once it stops fusing helium in the core, once it stops fusing hydrogen to helium in the core, will begin to collapse, and that causes helium to fuse together to form carbon and some oxygen. And then you have shells appearing in a star. Now, because this outward pressure is so much more greater than hydrogen to helium, helium to carbon and oxygen has such a much more massive energy release that the star swells up in size. And so if we look at the Hertzsprung-Russell diagram over here, as these stars begin to become to the end of their life, they stop fusing hydrogen, they begin to collapse, but then they have the secondary fusion of helium into carbon and oxygen, then they swell up and they leave the main sequence and they go to a region of this diagram over here, and they become giants, red giants, sometimes yellowish giants. Please note these ones over here, these are big blue stars, those are on the main sequence, they're still doing the regular fusion of hydrogen to helium, but these ones over here have left the main sequence, they are now fusing helium into carbon and some oxygen. And that causes the star to swell up. It's reckoned that's what's going to happen to our star. Once it reaches its end of its main sequence equilibrium, it will begin to collapse, but then swell up again as it does helium fusion into carbon and oxygen. And it's reckoned that the Sun might swell up in size to around the orbit of Venus. It might get to us on Earth, but we doubt it. But as that happens, it will get dimmer on the surface, but it becomes so much more massive that obviously it will boil us on Earth. We won't be around. We reckon our star will have another 5 billion or so years left on the main sequence. Okay, so when a star leaves the main sequence, it becomes a giant. Now, supergiants. What's going on there? Well, if we go to this diagram here, our Sun's over there, and it will stop fusing hydrogen, it will collapse, but then have the secondary fusion for helium into carbon and oxygen, swell up to be a red giant, and then eventually, once all of the helium that's available at the hottest part is used up, then it becomes a white dwarf. But not before all the hydrogen and the helium and some of the carbon, not before that becomes what's called a planetary nebula. So if we look at these brilliant images here, these are the leftovers of a star. And let's pick this one here. You notice at the centre of it there's a little white bright light. Now that is actually the core of the star. It's no longer doing fusion, so that's actually a carbon ball. Super hot, super bright. That is the core of the star, emitting light and heat as a star normally does, but it's not fusion anymore. It's a white dwarf that's cooling. And the gas that was part of the Sun, so because it's no longer doing the fusion, the star's so big that the gas just sort of blows away into the surrounding area, and it forms these wonderful gas clouds called planetary nebulas. Okay, the Cat's Eye Nebula is quite a famous one, but at the centre of it is a white dwarf. Now these would be nebula of hydrogen, helium gas, maybe some other bits in, some carbon, some oxygen, but those are the leftovers of a star. So here in this diagram we should know why it leaves the protostar stage, what happens at the main sequence, why it swells up and becomes a red giant, and then once the fusion of helium stops, that's it for that star. It's not big enough to start fusing carbon, so it just stops fusing and the star just blows away, becomes a planetary nebula, leaving behind a white dwarf. That is a super hot carbon core which will glow for hundreds of billions of years, but it is cooling. And in some time in the far future of the universe, those white dwarfs will cool down enough to be black dwarfs. But we're talking way in the future, an unimaginably long number of years in the future. Now, over here, we have a big star. And just like the main sequence star over here, it fuses hydrogen into helium. And just like the main sequence stars over there, that will stop. And as it stops, it will begin to collapse. And then it will have the secondary fusion of helium into carbon and oxygen, and the star swells up. But because the star is so huge to begin with, something happens with this star. Because this star here, once it stops fusing the helium into carbon, it's still big enough and hot enough in the middle that as it begins to collapse again, it will fuse the carbon and oxygen into more and more atoms. Neon, silicon, bigger atoms. And that process will happen again and again and again and again until you have half a dozen or so layers. So you have you'll have hydrogen, you have all these different layers going all the way in. The core gets smaller and smaller and smaller, but you have hydrogen, then helium, then carbon, then neon, some oxygens in there as well. You go all the way down. At the core, you'll have iron. You have fused heavier and heavier elements into an iron core. At this stage, the star is massive. Going back to our diagram, these super red giants are stars that were big to begin with, and as they've left the main sequence and gone through various stages of fusion, they have become so huge and such massive stars that they have these many layers of gas and elements, from hydrogen all the way down to a large iron core. Now, there's a problem with iron, because just as we can fuse hydrogen into helium and helium into carbon, we can do that with enough temperature or enough confinement. We cannot do it with hydrogen, with iron. This is actually the hardest atom to fuse. Okay, we cannot, or it's virtually impossible to fuse iron together in this situation here. There's not enough energy, not enough confinement to do that. The temperatures are, even though they're phenomenally high, they're not high enough to fuse iron. This is the hardest atom to fuse to itself. So what happens? Iron can't fuse together, so fusion in this star stops. Now, whereas in here, these shells of gas just blew away into the surrounding neighbourhood, becoming a planetary nebula, this one here, something else happens. Instead of just blowing away into the surrounding area, this will collapse because it's so dense and so huge. The gravitational pull is so massive that the outer region of the star begins to collapse in a matter of seconds. And that collapsing causes a shock wave which bounces off the core, and as the shock wave bounces back out, it meets the collapsing layers of the star. You have this collision of gas and a shock wave. You have a huge, ridiculously bright and powerful explosion, and that explosion is called a supernova. Okay, a supernova. The supernova happens when big stars that were big in the main sequence, as they do the secondary and tertiary and further levels of fusion, once it gets to the iron core, it stops fusing and it collapses in seconds in a massive explosion, and then you have this ridiculously powerful explosion called the supernova. Now, we'll discuss these little bits in a second, what happens after the explosion, but I want to just mention something quickly inside the explosion, because over here in regular stars the biggest atom it's made is carbon, but over here this is where atoms are made from iron all the way up to uranium. Okay, uranium is 92, 238, the heaviest naturally occurring element and that we know of in the universe is uranium. That is made inside or during a supernova explosion. So all the things that we find on Earth, if we were to dig up the rocks on Earth, you know, we have everything from iron, copper, aluminium, we have ores of uranium, all the metals that we can find on planet Earth that are bigger than iron were only made during a supernova explosion. Okay, now why are they found on Earth? Well, listen, that's a question I'm going to try and answer somehow, in some way today or just now, but I want you to understand this. Regular stars end in a planetary nebula with a carbon core called a white dwarf. Big stars that become super red giants will end their existence in a supernova explosion. Most of them do. And as well as all these gas layers being ejected in a massive explosion, you've also got the energy hot enough and powerful enough to make further elements down as far as uranium 92. Now all that stuff is ejected into space to form what's called a nebula. Not a planetary nebula, but a nebula after a supernova. Now these are thousands of light years across. Okay, so these are massive clouds. They're still mainly hydrogen gas with helium, carbon, so on and so on. But they're mostly hydrogen, but they have everything in there, even down as far as uranium. Now, Earth. Where does that come in? Well, it's reckoned that the Earth, in fact the Sun, is at least a second generation. And what we mean by that is because you've got the Sun, and then you have Mercury, and then you have Venus going around the Sun, and then you have Earth going around the Sun. And on Earth we find everything from hydrogen all the way up to uranium, including carbon, oxygen, iron, silicon, so on and so on. All these things were made inside a star that's dying. These ones are made inside a dying star, but these ones here are only made inside a supernova. So it is reckoned, it's postulated, theorized, whatever you want to call it, that our Sun, the protostar that became our Sun, happened to be made in a nebula that was left behind after a supernova. So imagine early universe, a big star is formed, it goes through its life cycle, it explodes. Of all the stuff that's left behind and ejected into space, a lot of that hydrogen gas forms a new star called the Sun. And a lot of the material, all the dust and the rocks and everything that was captured in that gravitational pull, which includes all these elements, they form the planets. And this little rock here has all these exotic elements in there, but they came from a supernova explosion. So our Sun was made in the aftermath of a star that exploded. Now when you think about it, all the carbon that's in your body probably was made during a dying star, and eventually that star exploded, and all the atoms that make up you and our world and the computer that you're looking at this through and this pen, my hands, many of those atoms that I take for granted inside me and the machines that I use, they were made inside not just a dying star but an exploding star. I find that quite fascinating. Now, let's go back to this. We have a supernova. Let's just get out of the glare of the sun. The sun. I'm sun crazy, the light. We have a couple of options. Okay, we have a neutron star and a black hole. These are the remainders of the supernova explosion. It wouldn't be right to call them iron. It's not really the iron core, it's some strange version of iron that we don't quite understand. The laws of physics that we know about kind of break down a little bit in neutron stars and black holes. Neutron stars, where the atoms are so close together that its super dense, really huge gravitational pull. It's reckoned that a spoonful of neutron star material, if you were to drop it, then it would just cut a hole through the Earth. That's how strong the gravitational pull is for these neutron stars, where atoms no longer have the space between the neutrons and the nucleus and the electrons. That space is reduced almost to nothing. In a black hole, well, it's reckoned that even the situation neutron star is even more extreme in a black hole, where it's super dense and super massive in terms of its gravitational pull, that not even light can escape it. So these are the two ends of a big star once it's gone supernova. Now, what makes a black hole or a neutron star is based on the size of the leftover mass. If it's around, I think it's 1 to 3 times the mass of our sun left behind, it'll be a neutron star. Over that, it'll be a black hole. Again, this is theory. These numbers can change, but that's in general what we think. So, what do you have to know about for stars? You have to know how they're made, or how they're formed, how they're born. You need to know about what happens in the main sequence, what's happening to the star in the main sequence, and then both possible ends. What happens to a regular sized star as it stops fusing, and what happens here to become a white dwarf, and what happens to a bigger star as it becomes a super red giant, and eventually the supernova explosion. So what I'm going to give you then is an exam question where you have to take all the information, try and reduce it down into an answer that's easy to write and easy to explain. Try and reduce it down to perhaps a paragraph or 2 paragraphs. If it's a 6-mark question, try and reduce it down to something that you can answer concisely, and try and convey a lot of that information. Okay, some of the key words you would have to mention would be protostar, main sequence. You're looking at, you've got to mention this idea of fusion and the gravitational pull being balanced. You don't have to mention hydrostatic equilibrium, but you have to mention that there's a balance in the main sequence. You'd have to mention what happens when fusion of hydrogen stops, and what happens in smaller stars, and what happens to larger stars. And the eventual ends you have to know as well. You have to know what happens to a small star as it ends, and a large star, the 2 possibilities. Again, these depend on the initial size, or the size or the mass of the core that's left behind. Okay, so what I'm going to give you then is this diagram here. I'm going to give you this diagram here, and I'm going to give you this diagram here, which looks at the different stars in the main sequence in terms of their size, temperature, abundance, and then you have stars that aren't in the main sequence for various reasons. You have the giant stars, the supergiants, and then the white dwarfs. Okay, so lots to think about. I genuinely hope you enjoy the topic. I find it fascinating. I think stars are amazing things. The one thing I will say is that they are not on fire. They are not balls of fire in space. There's a thought to leave you with. Thank you for listening. I hope you enjoy the rest of your day, and I hope the work is enjoyable. So take care, and see you soon. Bye.